Welcome to 4 lectures on terpenes and terpenoids. In first lecture, we have seen the basic terminologies involved in terpenoid chemistry. We have also seen the classification as well as the applications of isoprene rule applied to the various structures of terpenoids. In lecture number 2 and lecture number 3, we have determined the structures of citral as well as geraniol on the basis of chemical methods of analysis along with the structure illustrations. In this lecture, we are going to discuss about the chemistry of menthol molecule. We'll discuss about its occurrence as well as uses. Structure details of menthol will be discussed in more detail on the basis of chemical methods of analysis. Synthesis as well as useful reactions of menthols will be discussed. Menthol is having a very rich stereochemical aspect, so we will discuss about the stereochemistry of menthol, and at the end we will discuss about the applications of menthol in kinetic resolutions of racemic mandelic acid. So first of all, let us see from where menthol we get. The major source of the menthol is a peppermint oil. These are the leaves of peppermint, and from these leaves we can isolate menthol in pure form. Menthol is a white solid crystalline compound with relatively lower melting point, that is 43 degrees centigrade. Menthol is having various applications, particularly more applications we will find in the medicinal field. It is used as local anesthetics. It is widely used to relieve minor throat irritations. Similarly, it is used in toothpaste, cosmetics, shaving gums, as well as toiletries. It is also used as chiral auxiliaries in asymmetric synthesis. The structure determinations of menthol was initiated in the year 1886. In those days, the chemists were not having sophisticated instruments, and therefore they were relying on the chemical methods of analysis. These chemical methods of analysis, that's a structure from menthol, was initiated from the determinations of the molecular formula. When carbon and hydrogens were estimated of menthol, then they reached to the molecular formula of the menthol, and it was found to be C10H20O. Molecular formula of the menthol is a very useful information about the structure of menthol. This molecular formula contains 10 number of carbon atoms, therefore it belongs to a class of monoterpenite. Monoterpenite class of terpenoids contains 2 isoprene units, and according to the special isoprene rule, these 2 isoprene units are joined through head to tail linkage. So we get a broad idea just by counting the 10 number of carbon atoms in the molecular formula of the menthol. Second information that we get from the molecular formula is the degree of unsaturations or the double bond equivalence. How many double bonds or how many rings is present in menthol, that is nothing but the degree of unsaturations or double bond equivalence. For a molecular formula CXHYOZ, the double bond equivalence is calculated by x plus 1 minus y by 2. So if you keep these values here, then the degree of unsaturation is found to be equals to 1 in menthol. Now menthol is having 1 degree of unsaturation. It means that menthol may be a monocyclic molecule or it may contain 1 double bond. So in a subsequent investigations, we have to address this. We have to find out this nature of unsaturations. That's a degree of unsaturations or a double bond equivalent. Now preliminary experiments have shown that menthol is a saturated compound. Preliminary experiments means, for example, bromination reaction. It does not add to the bromine. So chemists believe that menthol is a saturated molecule. So this degree of unsaturation 1 must be corresponds to perhaps monocyclic nature of the menthol, and we should have some chemical evidences in support of this assumption. Now let us find out the nature of oxygen. For this, menthol was treated with acetic anhydride in presence of pyridine, and it leads to form monoacetate derivative. Now the formations of monoacetate derivative, it means that the menthol is an alcohol. Alcohols on acetylation gives a monoacetate derivative, and therefore menthol is an alcohol. So we get a conclusion about the nature of oxygen, that menthol is an alcohol. Now alcohol is of 3 types: primary alcohol, secondary alcohol, as well as tertiary alcohol. Now the question is, what is this nature? So for that, the next experiment is performed. Here the oxidations of menthol was performed, and the resulting product is C10H18O. The analysis of this compound has shown that it is a ketone, and it was called as a menthone. Since we get in oxidation ketone, it means that our starting material, that's a menthol, which we have proved already as alcohol, must be of secondary alcohol type of the compound. So on the basis of oxidation experiment, we have now concluded that menthol is a secondary alcohol. In this way, we have proved now the nature of unsaturation is equal to 1. We have proved these are the structural features of the menthol. Degree of unsaturation is equal to 1. and the nature of oxygen is a secondary alcohol. So the molecular formula of the menthol can be written as C10H19OH, and the parent hydrocarbon of C10H19OH is C10H20, and this C10H20 corresponds to CnH2n. CnH2n means 1 degree of unsaturation again, and as we have already said that the menthol molecule is a saturated compound, we assume now that menthol is monocyclic in nature. So in this way, we have got these three informations as far as this discussions about the menthol is concerned. Degree of unsaturation is equal to 1, and it corresponds to the monocyclic nature, and here is a secondary alcohol nature of the menthol. Now it's a monocyclic compound, and what should be the nature of that cyclic compound, that we have to provide some chemical evidences. So here there are two chemical evidences: menthol followed by dehydration, because alcohols undergo dehydration, and dehydration, this product was subjected to dehydrogenation with sulfur or selenium and leads to form the paracymene. So the formation of paracymene again gives us a clue about the cyclic structure of this menthol molecule. Another evidence is coming from the reductions of menthol. Menthol on reductions with HI forms the paramenthone. So formations of paramenthone and the paracymene suggest us to assume this skeleton, that's a paramenthane skeleton of menthol molecule. So we have come a very long way as far as the structures of the menthol. We have proved that it's a secondary alcohol and this is a skeleton present in it. So if we attach this OH group in this skeleton, then we will get the structure of menthol. Now in this skeleton, it's a secondary alcohol. So in this skeleton, these are the only two positions which are secondary in nature. Rest of the carbon, this is a tertiary carbon. This is also a tertiary. This is also a tertiary. This is primary. This is primary. This is primary. So only these two positions are left. So OH is likely to attach here, or it is likely to attach in structure number 2. So the most probable structures of menthol can be either 1 or 2. So we have to now again do more analysis whether it is a structure number 1 or structure number 2. For this, in 1886 and in 1894, oxidation experiments of menthol were performed, and it is called as a oxidative degradations, or we can also say that's a graded oxidations. In this oxidation, menthol was subjected to oxidation using CrO3. We got a menthol. We have already seen these reactions. Now it's a cyclic ketone, and this cyclic ketone on KMnO4 oxidation leads to form keto acids, and it is called as a ketomenthelic acid. Analysis of ketomenthelic acid has proved that it is a keto acid, and this keto acid on further KMnO4 oxidations form 3-methyl adipic acid. Here 3 number of carbon atoms are lost, and it is in the form of acetone C10H18O3, and is a C7H12O4. So 3 number of carbon atoms are lost, and therefore it gives a clue about the presence of isopropyl group here, and the formations of the last product was found to be the 3-methyl adipic acid. So the formations of 3-methyl adipic acid gives us a clue to assume the structures of menthone here in this way. So this was the possibility here. This 3-methyl adipic acid formation is possible only when we assume the structures of menthone in this way. So here the bond cleavage is likely to occur, and then we will get here C double bond O, and then this will again undergo oxidations, and we will get here carboxylic acid. Now this oxidation sequence on the basis of this oxidative degradations varies to the structures of menthone, and therefore varies to the structures of the menthol here. So out of these two structure 1 and 2, the correct structures of the menthol is 2. Now once the structure of menthol is proved, we have to convince ourselves by writing the reaction sequence, what may be the actual case happening in this oxidative degradations of menthol carried out in 1896. Menthol on oxidations gives menthone. This is very simple to understand. And now here the carbon-carbon bond cleavage occurs, and we get a ketomenthelic acid. It's a keto-carboxylic acid. Keto-carboxylic acid again undergoes subsequent degradations, and here we get a degradation product. That's a 3 number of carbon atoms are lost from ketomenthelic acid, and it's in the form of acetone. and the another product is a 3-methyl adipic acid. So formations of 3-methyl adipic acid is possible only when we assume these structures of the menthol. The another structure of the menthol, that was another possibility. Here we cannot get this dicarboxylic acid. Here the other carboxylic acid is obtained. 1, 2, 3, 4 and 5 number of carbon atoms are there. Whereas here the carboxylic acid contains a 6 number of carbon atoms in a long chain here. So on the basis of oxidative degradation experiment, we have proved the structures of the menthol here. When the investigations of the structure of menthol was going, the chemists were having some literature report about the polizone. This is another monocyclic, it's a monoterpenite. This polizone on reductions again gives a menthol, and therefore this was a strong evidence in structure of in support of the menthol. The structure of polizone in those days were again proved on the basis of oxidative degradation experiment. One is a retroaldol condensation and second is oxidation, and again here 3-methyl adipic acid is formed, and again this 3-methyl adipic acid was similarly formed in this another oxidative degradation experiments of the menthol. So the polizone structure has given us a confidence to reach to the structures of the menthol. This is the positions of the OH group here. So in this way, we have elucidate the structures of menthol on the basis of simple chemical methods of analysis. The investigation starts with the determinations of molecular formula of the menthol. From molecular formula, we have seen that it is having 1 degree of unsaturation. Then the nature of oxygen was proved to be an alcohol by monoacetate formation reactions. Then its nature secondary alcohol was found on the basis of CrO3 oxidations. Then skeleton nature of the menthol was proved from two experiments as HI reductions as well as dehydrogenations with dehydrogenations leading to form the parasamine. And then uh, the nature of this OH, where this OH group is present either here or here, it was proved on the basis of oxidative degradation experiment, where the final product is a 3-methyl adipic acid. So formations of 3-methyl adipic acid is possible only when we assume the structures of menthol here. In alternate way, we have seen in previous slide that this 3-methyl adipic acid is not formed. So in this way, with the help of very simple chemicals, chemists at that time we reached to the structures of the menthol molecule. Now after the structure determination, now it's time to synthesize in the lab, and synthesis of menthol again gives the support to the structure of the menthol molecule. Now menthol can be prepared. This was the synthesis reported in 1907. Starting from metacresol. Metacresol is treated with the isopropyl iodide. It is offering 7 number of carbon atoms and this isopropyl, and we get a menthol here. And here attachment of this isopropyl group is not straightforward in those days, because there was no, what we say, the development of the Friedel-Crafts reactions, and therefore chemists relied again on the carbanion chemistry. Metacresol on reduction. Now this synthesis can be learned, can be made interesting by transforming into problem that whatever the reagents are involved here: H2Ni reduction, oxidation, this diethyl oxalate, then base catalyzed alkylations, then distillations with the copper salt and reductions. All these reagents are preliminary reagents, and students generally know about it. And therefore, the synthesis of menthol can be learned in the form of this format also. So metacresol on reduction with S2 plus Ni gives 3-methyl cyclohexanol. 3-methyl cyclohexanol on oxidation gives 3-methyl cyclohexanol. And then here we have to introduce now isopropyl group, and for that we are trying to introduce here some active methylene compounds just like a ethyl acetoacetate. So for that diethyl oxalate reacts with sodium metal, and we get here 1,3 dicarbonyl type of the compound, and when this is heated it eliminates the carbon monoxide. So this is a cyclic beta ketoester, and just like ethyl acetoacetate, it's a cyclic beta ketoester, and here we can achieve the alkylations very easily. Its reactions with the sodium ethoxide followed by its alkylations with the diisopropyl iodide forms here alkylation products. So in this way we reach to our main skeleton of the molecule, and we do not need this, and for that they have performed its reactions with the sodium ethoxide, and it leads to the ring opening reactions here. This dicarboxylic acid forms a calcium salt, and if this calcium salt is distilled, it leads to form the menthone. And menthone reductions gives us menthol here. So this is a very interesting synthesis of menthol involving very simple starting material like metacresol as well as isopropyl iodide. Now in this reduction of menthone to menthol, we get isomeric. There are three stereochemical centers. So menthol is not enantiomerically or stereochemically it is prepared here. So another synthesis, the naturally occurring menthol is having a levorotatory nature. So minus menthol is here, and this synthesis of minus menthol was accomplished in the year 1976. The route is very interesting to discuss. The first step here is the Prederkraft alkylation reactions using aluminum alkoxide. It leads to form thymol. Thymol on reductions gives this menthol molecule. So this is a very shortcut method in fact, but here the biggest problem is that this menthol contains three stereochemical centers, and because of these three stereochemical center, it exists in various stereoisomeric form. Then on this there are various isomers of menthol, and they are having different boiling point. So they are diastereomers, and these diastereomers on fractional distillations leads to form here menthol molecule. And menthol is again a mixture of minus menthol and the plus menthol. So this menthol was separated from menthol, isomenthol, neomenthol, neoisomenthol. Now these two are separated by simple reactions. Its transesterification is made, and we get again these two. And these two were separated by adding a pure form of one of the isomers, that is called as crystallization by seeding. And then here minus menthol, there's a levomenthol crystallizes out, whereas the plus menthol is in the flask, is in a mother liquor. So in this way, the overall yield of the minus menthol was achieved around 90%. So the another first synthesis was reported in the 1907, and after almost 70 years, this was a enantioselective synthesis. Uh, Here the synthesis of one isomer of the menthol was discussed. Now let us see the preliminary reactions of menthol. Is a secondary alcohol on PCl5 methyl chloride. This on oxidation gives menthol. This on oxidation gives a carbon-carbon bond cleavage. It proceeds to the intermediates of menthone. We get keto carboxylic acid. It is called as a ketomenthilic acid. Similarly, it undergo dehydration reactions, and we get a 3-menthene. This is a esterification reactions developed by Eli, and this esterification reactions of menthol results in the formations of ester, and menthol was found to react more faster than isomenthol, neomenthol as well as neoisomenthol reactamic compounds. Mandelic acid exists. Now let us discuss the stereochemistry of menthol. In the structure of menthol, there are three chiral centers, and because of these three chiral center, it exists in 2 raised to power 3 or 8 number of stereoisomers. These 8 stereoisomers are shown here. In other words, menthol molecule exists in 4 pairs of enantiomers, or we can say 4 racemic modifications, and these 4 racemic modifications are of menthol, isomenthol, neomenthol as well as neoisomenthol. Menthol is having its 2 isomers. Similarly, isomenthol, neomenthol and the neoisomenthol will have 2 enantiomers, and we can 2 stereoisomers, and we call them as a enantiomers. Now this menthol is a diastereomer of isomenthol, is a diastereomer of neomenthol and the neoisomenthol. In similarly, the isomenthol will be the diastereomer of remaining molecules, that's a menthol, neomenthol as well as neoisomenthol. So to understand the concept of enantiomers as well as a diastereomer, the examples of menthol can be demonstrated for discussion. The naturally occurring menthol is levirotatory, and its configuration is found to be 1R, 2S and 5R. Now this isomerism is possible because three substituents can exist with respect to each other either in a cis fashion or they can be trans with respect to each other, and therefore there are 8 total stereoisomers of menthol. Now since it's a 6-membered ring, menthol is a 6-membered ring, we can draw chair conformations of this menthol, isomenthol, neomenthol and isomenthol. While drawing the chair conformations, this bulkier isopropyl group will prepare to occupy an equatorial position. This is the most bulkier substituent amongst methyl hydroxyl and the isopropyl. Therefore, it will prepare to occupy an equatorial positions which is just less sterically hindered. So in all these cases, we have written the isopropyl group in the equatorial position, and accordingly we have adjusted the positions of hydroxyl as well as OH. In menthol, all the substituents are equatorial, whereas in the remaining, at least one substituent. In isomenthol and neomenthol, there is only one axial substituent, whereas in case of neo-isomenthol, we are having two bulkier substituents which are axial with respect to each other. And because of 1,3-diaxial interactions, the isomenthol, neomenthol, and the neo-isomenthol, they will be unstable compared to the menthol. On the right hand side of this equilibrium, we have shown the isopropyl group in a axial positions, and definitely this is the most unstable conformations of all these four molecules, four isomers, and therefore these molecules menthol, isomenthol, neomenthol, and neo-isomenthol will prepare these conformations where the isopropyl group has occupied an equatorial positions. Now, as far the stability is concerned, the menthol is the most stable because it has occupied, there is absence of 1,3-diaxial interactions. However, one Gaussian interaction is here. Neo-isomenthol is the least stable because there is a 1,3-diaxial interactions between two bulkier substituents OH as well as methyl, and therefore these are least stable. Now, among these two, there is one axial CH3 as well as OH, but this isomenthol is unstable compared to the neomenthol because there is a Gaussian interactions, and because of this Gaussian interactions as well as 1,3-diaxial interactions, it is at the third position as per the stability of the order is concerned. The neomenthol is having only one 1,3-diaxial interactions. So stability order depends upon the 1,3-diaxial interactions, as well as here isopropyl group has occupied the equatorial positions. Menthol is the most stable where all the positions have equatorial. Now these conformations of the isomenthol, here is again summary we have written. The methyl group is equatorial here. Now in this most stable conformation, the OH group has occupied here equatorial. It is here is also equatorial. But in this new menthol as well as a new isomenthol, it has occupied axial position. Hydroxyl group has occupied the axial positions. So if you perform some reactions of the hydroxyl group, then there will be definitely some reactivity difference. So the conformations of this various stereoisomers of menthol has again got some additional evidence from the work of Ely. Ely performed a simple esterification reactions of all four stereoisomers of menthol, and he found that the menthol is the most reactive of all and neo-menthol is the least stable. Now esterification of hydroxyl group here is taking place. The equatorial group, if it is at the equatorial position, then the esterification will be more prepared rate of reactions will be there compared to its axial position, because in equatorial there is a less steric congestion. Now if you look at the menthol, it's in equatorial positions and all the substituents are also equatorial, and that's why the menthol reacts fastest. Whereas for new menthol, this is not a stable structure. We have written a equatorial position of OH. In previous slide, we have written two conformations of the new menthol where the isopropyl group has occupied. But here now we have written equatorial positions of the OH, and as a result of that it becomes axial here, and since this is an unstable structure because of strong 1,3-diaxial interactions, its concentration will be effective concentration. This new isomenthol will not prepare to stay in this conformation, and therefore the rate of esterifications will be the least. Sorry, it will be the least in case of new menthol. If there are two 1,3-diaxial interactions, here there is only one 1,3-diaxial interactions, and here again there is a 1,3-diaxial interactions. So among all these four conformations, the esterifications of equatorial OH is occurring, but apart from that, the other factors 1,3-diaxial are also taken into consideration, and therefore the menthol is reacting most faster than that of the isomenthol. Isomenthol reacts faster than the new isomenthol, and the new menthol reacts least. Now let us consider the elimination reactions of the menthol. We have written the two structures of methyl chloride and new methyl chloride. It is observed that methyl chloride reacts faster compared to the methyl chloride reacts slowly compared to the new methyl chloride. Methyl chloride exists in this conformation where all the positions are equatorial. But for the elimination reactions, the anti-peripheral arrangement of the chlorine as well as hydrogen is required. It is lagging here, and therefore it will try to adopt this conformation where the hydrogen and Cl they are anti to each other. But this isopropyl group and the methyl they are at the axial positions and they undergo 1,3 diaxial interactions, and as a result of that, this is a very least stable. It will not, this more stable conformation will not undergo these conformations very fast, and since it is slow, the overall rate of the elimination is also slow. Whereas in neomethyl chloride, we are having Cl in axial positions. There is a 1,3 diaxial interactions, and there are two trans hydrogen with respect to chlorine. And bulkier isopropyl group as well as the methyl group, they are occupying the equatorial positions, and we get two elimination product. This is a set product. This is a more substrate product. This is forming more quantity compared to the less substrate is a set product. So this chlorine is having two hydrogens here, which is trans to each other. This chlorine is having only this hydrogen, but for that it has to adopt a this conformation which is unstable, and as a result of that the methyl chloride will react slower than that of the neomethyl chloride. Is having one. Now let us consider the applications of levomenthol in the kinetic resolutions of racemic mandelic acid. Mandelic acid is having one chiral center, so it exists as enantiomers. It exists as a racemic mixture here. The racemic mixtures of mandelic acid can be separated into two individual isomers, as a plus isomer and the minus isomer, by reactions with levomenthol. So when the chiral reagent is treated with the racemic mixtures of the mandelic acid, then then these two isomers of mandelic acid shows a different behavior. The one isomers of the mandelic acid plus form of the mandelic acid reacts with the menthol at a faster rate to form this ester, whereas the minus form of the menthol, that's a levo form of the menthol, remains unreacted. So as a result of that, the plus menthol is converted into a ester, which on hydrolysis we get plus mandelic acid, and unreacted mandelic acid, whatever is left, is a minus mandelic acid. So in this way, we can achieve here the separations of plus mandelic acid as well as minus mandelic acid using the menthol chemistry here. Menthol is a chiral reagent, and it reacts in a very differentiating way with the two isomers of mandelic acid, and therefore because of the rate difference between these two isomers, we get the separations of plus mandelic acid as well as minus mandelic acid using menthol. We are right from the beginning. Let us see the first of all revision, and then we will conclude about it. So we started for the structure determinations with the help of very preliminary experiments, and we reached to the structures of the menthol. Here the formations of 3-methyl adipic acid is a turning point of investigations, as well as the clue from polygen chemistry is also giving us the structure of menthol molecule. Then another one is about the synthesis of menthol. Here it can be accomplished through metacresol as well as the isopropyl iodide here. Just to introduce this here, we have done some carbanion chemistry here. And then at the end we get a menthol, and its reductions gives a menthol. And this reduction gives a lot of stereoisomers of the menthol. Therefore the synthesis of minus menthol was levomenthol was accomplished in year 1976 from metacresol. So this is, it exists in a various isomers. This on fractional distillations gives racemic mixture, and these two were separated by crystallizations by seeding. Then this is a very interesting part. Menthol shows isomerisms, and isopropyl group prefers to occupy equatorial positions, and it is having an influence on the esterification reactions. Esterifications of equatorial OH is faster, and in that case it is amply available here. This is also available. But the remaining these two, even though it is available, the stability of these two conformation is very less because the isopropyl group is at the axial positions. These are elimination reactions and the kinetic resolutions. Now, once this menthol chemistry is learned, we have to check how much we have progressed, and for that it is necessary you should solve the problems. Now, what is the quality of the problem, or what may be the type of the problems we have to undertake is here about the stereochemistry of menthol. How many chiral centers are there? You must write the various stereoisomers of menthol and relationship of each isomer with the another isomers. Then the reactivity order, conformational analysis of all these isomers of stereoisomers of menthol we have to discuss, and This has indirect effect on the esterification reactions using dinitrobenzoyl chloride. The third problem is related to the 3-methyl adipic acid formation, oxidative degradation experiments, and here the products of the intermediates are shown, and therefore this is a very interesting exercise to solve. The mechanism of elimination reaction students should learn here is anti-periplanar eliminations, and here chlorine occupying this axial position gives isopropyl in a isopropyl group in a axial position, and that's why the rate of the reaction is very less. Whereas here neomethyl chloride, there are two hydrogens anti to the chlorine. Here is one hydrogen and here is another hydrogen, and we get the two products. And this is the last one is all about the synthesis of the menthol. So in this way, we have learned the chemistry of menthol. Now, in the next lecture, we'll talk about the chemistry of alpha terpenol. Thank you. Thank you very much for watching the video.